Hello and welcome back. Let's talk about series. So what is a series? Well, a series is represented this way with a capital sigma from, which represents sum from n equals some value, let's say 1 to infinity. And we'll use a sub n as our example. We can think of a sub n as a sequence that we learned about last video. And this is just the sum of all the terms in the sequence between these bounds. So it's very simple. Instead of the sequence, say A, B, C, D, we have A plus B plus C plus D. Very simple concept, very interesting applications, I guess you could say, very interesting problems we see with these. But let's just talk about them. Well, we know that we have a few series. We have, for example, we have infinitely many series. I shouldn't have just said a few. But for example, we have the sum from n equals 1 to infinity of, say, n. And, I mean, we all know this is going to equal infinity. I want to represent this in a bit of a strange way. I'm going to say this is 1 over n to the negative 1. This is the same thing. But I just want to represent it that way. We also have the sum from n equals 1 of 1 over n squared. This doesn't equal infinity. And so what you might notice is we have very similar concepts to improper integrals, and the truth be told, they're very similar to improper integrals. And this is a divergent sum, and this is a convergent. And this actually equals to about 1.6 something. I'm not exactly sure. But let's just hop right into it. So why I know that this is a divergent sum and this is a convergent sum is because we call these P series. Where we have the sum from n equals 1 to infinity of n to the power of some value p. And the cool thing about P series is if P is less than or equal to 1, it will be divergent, such in this case, negative 1 is less than 1, and that's why I wrote it that way. And if P is greater than 1, it will be convergent, just like here. 2 is greater than 1. So that's the first trick we can use to know if a sum is divergent or convergent. And often that's going to be what we want to know because it becomes very hard to evaluate the sum of infinitely many numbers. In many cases, it's impossible. So let's get into a second trick that we have, and that is going to use this same notation that we used at the start of the video, where this is thought about as a sequence. Now, if we take the limit as n approaches infinity for our sequence, we remember this is called a limiting value from the last video. Well, if this limiting value does not equal 0, our sum will be divergent. And that's very easy to see when you graph these things. Say we have a limiting value at 1. I'll draw my line of 1 here. And we have our series come down. And each of these dots is a term in the series. Well, we're always going to be adding these numbers infinitely many times. Infinitely many ones is infinity. infinitely many of any number is going to be plus or minus infinity, and that is the definition of a divergent sum. Let's make sure to not use this the other way around and not say that as long as the limiting value is 0, it is convergent, since that's not the case. For example, the limit as n approaches infinity of 1 over n equals 0, but the sum of 1 over n equals infinity from n equals 1 to infinity. So that's that. That's that very easy test, but a lot of the time that's not actually going to tell us anything. Let's look into the improper integral test. Now, at the start of the video, I said that these share a lot of properties with improper integrals, and it's true. Let's just go back to our example, 1 over n. Well, what we can do is we can take the first term in the sum, and we can say this equals about the first term in the sum, which is 1, because 1 over 1 is 1, plus the improper integral with the same bounds of, let's say that defined as x. We know this integral is infinity, and so what we're going to get is infinity. And this is infinity. So this can tell us if this is a divergent series. It also can tell us if it's convergent, and what happens is if this integral is divergent, this sum is divergent. If this integral is convergent, this sum is convergent. The thing about it being convergent, though, say the example of 1 over n squared, is that this can actually estimate our sum for us, and in this case, this would equal 2. It would be 1 plus 1. This would be 1. So yeah, the actual value of this, like I said earlier, is about 1.6, so we're not super far off. And it's a pretty good estimate. So that's the improper integral test. We can see if it's divergent or convergent, and if it's convergent, we can estimate the sum. Obviously, if it's divergent, we know the sum. It's plus or minus infinity. So next we've got the comparison test. We remember the comparison test from improper integrals. We can test if something is divergent or convergent. And it's essentially the same thing, so I won't go over too much, but we'll just go over an example. The sum from n equals 1 to infinity of 1 over n squared plus e to the n. Now we know that 1 over n squared, that's a convergent sum, and it equals about 1.6. And we know that if we add something positive, keep in mind e to the n is always positive, to the denominator, we're going to get a smaller number. So we can complete this inequality here, and we can say that this is less than 1 over n squared, and the sum from n equals 1 to infinity of 1 over n squared is convergent, so this must also be convergent. So we're starting to see now, these are very similar to improper integrals. Let's get into another test. Actually, our last test. We call this the ratio test, and this one's often used for alternating series. We looked at alternating sequences last video that go like this. They bounce up and down, basically. And alternating series can still be convergent. They can also be divergent. They can also be undefined, which is pretty annoying. But, yeah. So, what the ratio test tells us is that if we take the limit as n approaches infinity for a sub n plus 1 over a n, absolute valued, we can get a value, and it can tell us something about what exactly this sum would do if the sum was sum from some value of a sub n. And so all we need to do is think of this as a function basically and plug n plus 1 in wherever we see n. And so what this tells us is that if this limit equals 1, it doesn't tell us anything. If this limit is greater than 1, we know that a sub n plus 1 is always greater, meaning that the absolute value of each term gets greater on a graph. So it's going out like this, or out like this, or doing both. And that means it's divergent, obviously. Similarly, if it's less than 1, it's going to be convergent. So let's look at an example. We have the sum from n equals 1 to infinity of negative 1 to the n over n squared. Remember, this negative 1 to the n is going to alternate this. It's basically going to be a amplifier for our series of 1 over n squared, and the amplifier is going to go up and down and up and down. It's going to go all over the place. But what we can do is we can say that this is our a to the n. Our a to the n plus 1 is just going to be negative 1. We see an n, we put an n plus 1. Over, we see an n, we put an n plus 1, and we squared our n, so we square our n plus 1. Let's take the absolute value of this a sub n plus 1 and put it over a to the n. This is going to be negative 1 to the n plus 1 divided by n plus 1 squared. Let's put some brackets around it to make it more clear. Negative 1 to the n over n squared. Okay, this is looking pretty easy. Negative 1 to the power of some integer is either going to be positive or negative 1, and the absolute value of plus or minus 1 is 1. So if we're multiplying by 1, we can just completely get rid of that. So what we've got here is now, let's just get rid of this, make it 1. Let's just get rid of this, make it 1. Well, that's easy. We can just take this down to the bottom of a single fraction, take this up to the top. We've got the absolute value of n squared over n plus 1 squared. Let's take the limit as n approaches infinity of this. That's n squared over n plus 1 squared. Well, we can actually take these squareds out, since both terms are squared, and take it out here. We know that this is going to be 0, so it's going to be 0 squared, which is 0. And since 0 is less than 1, this is a convergent series, which makes sense because our series is going to look like 1 over n squared, just bouncing back and forth. And we know that 1 over n squared is convergent due to the p-series. So that's series. Thanks for watching. I hope to see you in the Taylor series season finale for Calculus 2 until we hop into some very exciting stuff in Calc 3.